So what we're doing is whatever object that we've got, so like I'll draw something ambiguous, and I'm going to draw something incredibly ambiguous. So we have a 3D shape. So now that we've got the 3D shape, and you've seen the waffle, right? You've seen what the outcome is. If I were to draw the plan of the waffle, how would it look?
Grid.
Yeah, just look like a grid, right? So if I, like in plan, it would look roughly like so, yeah? And what's important about this grid is that it is actually orthogonal, okay? Because when we laser cut, the laser only cuts in one angle. And so the outcome of that is you're always going to end up with a slot that is orthogonal or perpendicular or normal to the surface face that you're working with. So that means when they slot together, we want it to be 90 degrees. So let's step through, what do we want to do with this object? Like, how would you do this manually?
We just cut it in segments and then in the section view. And then
Yeah, so you want to create a section of this object.
Yeah.
Is there another word for section that might have a suffix, a prefix to it that is a function that you could apply to an object? Such as intersection, yeah? So if we do an intersection on this object, we're going to get a result. Now, what type of object could I intersect with a 3D B-wrap that would therefore create like a flat outcome? Huh? A plane, right? So planes are 3D infinite flat objects. So if I put a plane here, then even though it doesn't look like it's intersecting, I can run a mathematical intersection and that will then give me that. So if I create an intersection between a line and a plane, what would the outcome be? A point, yeah? So if I were to create an intersection between a plane and a surface, what type of outcomes could I get? I could get curves. I could also get, this is an edge case, pardon the pun, but if I have a bit like a surface that goes to there, and I have a plane that runs through that, what type of outcome would I get? Yeah, I could get points as well. So very rare to get a point, but what we're interested in is getting curves, yeah? So if I've taken a plane and I've intersected it, I'm only getting one section, right? So if I want to complete the waffle, what do I have to do?
do it over and over again.
Yep. So if we do it over and over and over again in one direction, that's going to give us these sections, right? So if I just pick one of these out, I'm going to pick out this one. The outcome of that is going to look like this, yeah? And then if I do it in the opposite direction, 90 degrees. So here's my planes. Then if I pick out one here, so the intersection that would roughly go through there, then I would get a shape that looks like that maybe, yeah? So I know I've made a face. At least it's not a dick. Okay. So if I've now got these two sections. If I try and laser cut them, we've got an issue, yeah? So we've got to start doing our slots to actually piece these guys together. So at the point that we actually have our intersecting curves, the curves that come from the intersection, we need to then also start finding where they intersect in the opposite direction, right? So the lines that I've just drawn right now are the lines that the opposite direction actually touches. So at that point, we've got lines. If I were to then turn them into slots, what do I have to do? Like if we just focus on this one, if I had this list of lines and I need to turn them into slots, what's the first step? Have a guess. There's no wrong answer. There is, but it's okay. You could be wrong.
We have to like offset each line.
Okay, that is a step, but it's probably not the first one. Find the midpoint. So we need to basically split these in two, yeah? Now if we find the midpoint, that's going to give us a point. What we actually want as an outcome is, if I draw a slot line, we actually want half the line, yeah? So is there a component that we've used that breaks lines down? Yeah. Okay, so we could shatter this, and at what coordinate would we shatter it?
50%.
So, and the important thing we have to do to the line to make it 50%? Yep. So we're going to reparameterize the line and shatter it at 50%, therefore giving us, let's say, the top, yeah? So just to reiterate, when we shatter it, we're going to get a list of lines, so I'll break them apart. So if this one is item 0 and this is item 1, then we can pick out the top one just by picking out item 0, yeah? So therefore, that will give us just the lines for the top. Then we can offset them to give them thickness and then connect them up to effectively create slots in our object. Now, if we did that on the other side, what's the only difference in that process that we should need to take?
You'd be offsetting item 1 instead of 0.
Exactly, right. So we don't pick item 0, we only pick item 1, which is then going to give us the bottom. Cool? Okay, there's going to be a few little tricks in here that I'm going to throw in, because we're going to start talking about branches, because, that's right, I dropped the lid, didn't I? Oh no, I didn't. Because at the end of the day, if we're thinking about this in 3D, there's an issue, right? We want this to then orient to a 2D environment. But we need to start orienting things in like an intelligent fashion with this so that they stay in the same location, blah, 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 okay? And we're also going to start putting labels on our outcomes because we might end up with two shapes that look a lot like this. And we want to know, okay, this belongs to A, and this is B, and let's say in the opposite direction, this is 3, right? So that we know when we cut it, we can put it together. So there's actually a cool little technique that you can take that we might not code today, but I'll at least point you in the direction of how to do it manually. But you can actually label these without anyone being able to see the labels when it's finally assembled. Where do you think you would put the label so that it would be invisible once it's assembled?
On the joint.
Yeah. So you can write your label in where the slot would effectively go, and it just disappears. Cool? I've seen people do waffles and they've gone B, and it's like, come on, guys.
You just said you get more marks if you label though.
Huh?
You just said you get more marks if you label,
Yes.
but not visibly.
If you get even more marks if you label and also make it so that you can't see it in the final product. When I say I want to see labels on your laser cutting,
You want them on the.
I want them on the view of the laser cutting document.
Okay.
Cool? But if you can design it so that it disappears, so good. And this particular assignment actually has a nice little open exploration task that you guys can play around with if you want, which is how do you make these slots work so you don't need glue without using friction? It's a nice little, if you can do it, I'll give you 100%. I like this. This is good. I'm going to do this for all these assignments from now on. I'll put in a little like, hey, if you can achieve this like extra goal, I'll give you blanket 100%.
Do you know how you said where they put the label on the inside of the joint?
Yeah.
How does it laser cut that? Because isn't it laser cutting flat?
What do you mean?
Are you saying so like when it, so you know how like you kind of joints like that?
Yeah.
Are they putting it in here?
No.
Oh, so they put it
No. If you put it on the flat surface there, when this piece of timber comes in and slots in, it's going to cover it up.
Yeah.
It's like people freak out when they see it. Like they're like, oh, all my labels are gone. Like like it's so good. I love it. I don't understand why it's so like mind bending, but yeah. Especially, I think it's when I've done it with clear acrylic, and because the way like the joints work and internal reflection, you still can't see it. So yeah, it's fun. It's good. This technique effectively allows us to create very complex shapes. So what we're going to do is we're going to use you guys have hopefully used the surface that we worked with last week. I'm just going to make a makeshift surface because it doesn't really matter so much what I do. It should be the same script. So
We're using last week.
Yep. It feels all nice and shiny now that I've got like my own version of Rhino. I feel all official.
Wasn't your company give you one?
Yeah, but it got like... I need to be connected, I need to be wired in to get access to it. And I'm here. And so, unless like we just sat around and I didn't teach, like that, it just wasn't worth it. Like I can't just sit here and be like, oh, I don't have a license. Sorry guys, you know? That's not professional of me. So I went and bought it. And it's tax deductible, so it's all good. I don't think it's tax deductible for you guys though.
Depends if it's
You gotta be
directly related to your work.
You gotta be working.
Yeah.
Yeah. It's probably smarter for you to buy the student version. It's cheaper. Okay, so whichever surface you want to work with, you guys probably want to deal with your trimmed surface, the one that we've actually, cut down and shaped to how we want it to look. And you could work with more than one. So you could do your full model, the one that's like everything all at the same time, or you can work on it piece by piece. So it's really up to you. But if you are going to work on the full model, you need to make sure that it is joined. So for example, if I quickly mirror this, if I've got two surfaces in Grasshopper that we want to do this process to, if you plug a panel in, you're going to see that there's two surfaces. In this case, we need to make sure that they're joined and a single surface. If you try and join them and it doesn't join and it still leaves you with two, then you've probably scripted your thing not perfectly. Like there's going to be issues, and I suggest you just do it in parts. Okay, so just, pardon? It's very hard to see. It's very dim. No, just rotate it more, man. It was just the angle. Just rotate it a bit. Much better. Yeah, so can you join all of those together into a single surface? Yeah, you can either, you can either work on a single one. Okay. I'm also just showing people so that, if they've got that issue, that's why.
So do I just hide everything and
Yeah, just hide everything and let's work on just a single one. And you guys will, this is actually a reason, remember last week how we shifted it so that it rotated a certain way? Like, so that it was pointing in the X direction? This is actually one of the assignments for which is the reason why we did that, okay? So what we need to do is generate planes that are going to cut through our object, okay? So quick and easy process for that is, if we can generate planes along the x-axis of our object that cut in the y, and we can generate planes along the y-axis that cut along x, that's going to give us our perpendicular system. By the way, there are actual triaxial, you can do triaxial or various other different types of waffles. So if you want to look into that, feel free to do that as well for this assignment. But that's exploration, okay? It's not something we can do in class. There's not enough time. Okay, so what we need to do is create planes in the x-axis. What component have we used that will take a preset minimum, maximum, and divide evenly between it? Yeah, right? So if we can create a range of points there, where are those points going to be spread out across? What's going to be, they're going to be going across the x-axis, yeah? So if we can create points with a variable x, let's grab bifocals. With a variable x, and we're going to grab a range that effectively plugs into that. We can see here that range of points going from 0 to 1, because the default range domain is 0 to 1. So what we want to do is extract data about this object to help drive this value. So the way to do that is by analyzing our brep. We want to deconstruct the brep's box. What that will do is it will look at the bounding box of your brep, and it will give you the domain of the x-axis, the domain of the y bounds, and the domain of the z bounds of that object. So as you can see, my object here goes from 0 in x to 33. And yours is probably going to be a number from 0 to a weird floating number, right?
Mine's just nil.
Yeah, mine's negative 140.
Okay, that's fine. Yours is nothing?
Yeah, so I'm 0 to I am negative 156.
That's cool, that's fine.
156.
That's fine. Okay, what that's doing is just telling you how where your object sits in space, okay? So if I've now got a domain, I can plug that domain into the domain of the range, and we can see that it's now creating points along my object in the x direction. That goes from the start to the end of that object. Cool? So what we're going to do first, we're going to work just on the x-axis, and then we'll move to the y-axis. So we'll just copy and paste what we're doing for the y-axis. So along the x-axis, we need to generate planes. Can anyone have a guess at the plane axes that we want to be working with? So if planes are made up of, like we can make up planes with two vectors and an origin. We've got these points as an origin. So what's one of the vectors that we can work with to generate the planes that we want? Are the planes going to be vertical? So what does that mean? What do you remember last week we were talking about, you know, if I said vertical plane, one of the vectors has to be Z? Yeah, so one of the vectors has to be up, right? So that's one. And what's the other?
Would be Y, wouldn't it?
Yeah, so if we go, like you can see here, the little icon here, we want to cut a plane through Y and Z. So if we jump to the vectors pane, and in the plane section, there's all these default planes, the default world planes. What we want is the YZ plane. And the beauty with these is if you plug points into them, it will place those planes at the points. I'm just going to shrink my planes down a bit. Sounds like there's a drone, but I reckon it's just a whippersnipper.
I think it's a drill.
A drill?
Yeah, it sounds like a drill.
Yeah, probably. Could be a whippersnipper.
I'm going to say topically it's a planer.
Huh?
It's a planer. I'm going to say topically it's a planer.
Okay. Pardon the pun. Yeah, it could be a planer. Okay. So we've got our planes. Has everyone got their planes? Excellent. Okay. So if I cut an open object, right? So see this object here, see how is this physically possible in reality? No, why is that? It's got zero thickness, right? So if I were to make this object, if I were to cut through it, get the curve, use that curve to cut into a piece of plywood, what would I end up with? Just a weird slot in plywood, right? Like I wouldn't end up with an actual piece. So we either need to do a process to that curve once we've defined it, like offset it and give it thickness, or we can make our object solid and then work with the solid object from there on. Okay, so we're going to do that because it's much easier. So we need to make our object solid. I'm going to do that just by extruding our surface with a nice Z vector. There are a billion different ways to make 3D objects, so you don't just have to use this technique, but this works.
Can you change the thickness on it?
Yeah, so the F value of the F factor will then, like if you put a slider into that, that'll change the thickness. Do you want me to zoom in?
So take it out of So we're cutting this in 3 mil.
Pardon?
Are we cutting this in 3 mil?
Yes, but that's the thickness of the sheet. That doesn't actually determine. So think of it like this. I can create a waffle piece that's this shape,
Yeah.
but your 3 mil thickness is actually that
Yeah.
that geometry. So it doesn't really, like, you don't have to make it 3 mil high.
Yeah.
If you did make it 3 mil high, you're probably in danger of having the whole thing just break apart as well. Yeah, I'll work with, what I'll do is I'll put in 10 mil. And therefore my object is too small. So if I show my object and make it bigger, you don't have to do this. Yours should be already. So if I scale this, the beauty of the system is because I'm measuring the length of it using this deconstruct box, I don't actually have to change anything in the script. It's responding to the size of the object already. Okay? Okay, so I've got my extruded object. What we're going to do is now run a brep plane intersection. Now, that is a mathematical intersection because planes are infinite. It's not a physical one. We're going to plug our brep in, and we are going to put our planes in as well. And we are going to run into a problem. If we check the output of our intersection, can anyone observe some things that we're not currently used to? With this output? Anyone? For one, the wire that we're getting as an output is dashed, and it's something that we haven't really explained. Yeah. So that dash is describing a list that has data in it that is branched. So can you see these little dark headers with the 0, semicolon 0, semicolon 0? These are called branches. And they exist in a tree, okay? So every list that we have in Grasshopper is actually a tree. Even if that list is flat and it doesn't have any branches, it's still a tree, okay? So this is a tree, and every branch in that tree has an address, and we can even see what they mean by a tree when if we grab the parameter viewer component and we plug data into that, if you double click that component, it will break it'll display that data in a tree fashion. So I've been talking about list data in various ways, right? I've explained it as a one-dimensional list, very similar to what we're seeing here in this, it just goes in like 1, 2, 3, 4, 5, right? Or 0, 1, 2, 3, 4, 5. I've also explained data as a loop or a circle, right? So the first item is also is to the right of the first item is item 1, and to the left of the first item is item -1, which is also the end of that list, right? Well, data can also be thought of as trees. And so what effectively is happening, the reason that this particular component is outputting these branches in a tree is because the outcome of each section might not produce one curve, okay? So just to sort of explain some of the rules of geometry in Grasshopper. Oh, something from last week. If if I draw a line, if I draw two lines, we've got two curves, yeah? If I connect them and actually join them, how many curves do I have? Like it's joined, so how many curves are there? One, right, correct. Okay. If they weren't touching, it'd still be one, right? And if these weren't touching, how many curves would I end up with? Two, okay. So curves have to be touching on their ends for them to join. If they don't touch on their ends, they won't join. Okay. I've drawn a donut. How many curves are there? Two, right? So there's no such thing as a hollow curve object. If I draw, an object that effectively has two holes in it, right? That's three curves. It's not one object with two holes in it. Yeah? If I made this a surface, yes, it's one object that's trimmed. But with curves, it's three. Okay, so if I made a Woolworths quality donut, yeah, and I cut through it, with this plane, how many objects did I produce? How many? So with this particular plane here, see, I've cut through two aspects. There's a hole here, right? So how many objects did I end up producing? Two. Right. So even though I've cut with one plane, I've produced two objects. If I cut with this plane, how many curves do I produce? Right. So what Grasshopper is doing is it's saying, hey, look, I know that I could produce more than one outcome here for each plane. So what I'm going to do is put them into little compartments that we're going to call branches, okay? And these branches effectively will contain all the objects that one plane would produce, okay? So it's just compartmentalizing them. Now, we're not going to run into the problem of generating more than one object per plane with this particular geometry, but you might if you do your full thing when a plane cuts along the edge, right? That's going to produce two. And that's when you're going to start seeing more than one object there. Okay, let's still keep looking at this. Two of these things are not like the other. What two of those are different?
Line-like curve.
Yeah, and the two line-like curves at the beginning and end. Okay, so what does that mean? That means we've got a curve that is literally a line. And are lines something that create objects when you actually cut them in a laser cutter? No. So what are these? Why are these there? They're the start and end, right? So remember, when we do the x-plane, when we get the x-bound of our object, what that's doing is getting the very, very, very end of our object, the very start and the very end. So that's only going to cut that to the point where it's literally like an infinitely thin object. So what's the easy way out? If you need to get rid of them, what's the easy way out?
Cull this time?
Yeah, let's get rid of them. Okay, and which items do we want to get rid of?
First and last.
0 and minus
Which
1.
is 0 and minus 1. Cool? Okay, let's do that. So when we can either cull the range, cull the construct point, or cull the YZ plane. So let's just cull it at the range, okay? So we'll go grab a cull index, and into that we are going to plug 0 and minus 1 as multi-line objects. And therefore, we lose our line-like curves. Past 10. We're good. We're almost on the home stretch. This is good. I can explain things better. Okay, we're good? So what do we get as an outcome? Let's just hide everything. And let's just look at the intersection geometry. We have our curves cutting through our object. Now do you remember from last week, what type of curves have we actually produced in theory? Do you remember?
Oh, yeah, I remember, well, sort of coming right.
Okay, if I cut a section through this particular object from this point to this point, what type of geometry would I produce? If I had to slice through this object from this point here to this point, I'd produce a line, okay? So in theory, if I'm going from this point to this point, what type of geometry would I produce from a hyperbolic paraboloid?
Well, geodesic curve?
No. You're right, it is geodesic, but it's not the answer I'm looking for.
Geodesic surface?
No. I'm making a parabola.
Yeah.
Remember? Do you remember? So if we generate a hyperbolic paraboloid, if we have a parabola going in one direction and a parabola going in the other, vertically, and repeating that, that will make a hyperbolic paraboloid. So that means if I cut through a hyperbolic paraboloid vertically, orthogonal to its topology, then I should get a parabola. Does that make sense? Yeah? Do you remember that from last week? Cool. It doesn't matter so much because this process can make whatever shape we want. It just, as long as it's planar, it's fine. And laser cutters are great at doing that. But the point being, I'm right now, like, these are parabolas. Okay? So, what are we going to do? I'm going to, if you are having issues, because I'm going to explain why branches are probably going to frustrate you a lot, okay? And it is purely to do with the way Grasshopper deals with its data. And you'll kind of, actually this is quite reminiscent of what I've already drawn on the board. Okay. So, if I have two lists of points, and if I do something to those points, such as like connect them, right? What's our outcome going to be? We're going to get straight lines between those points, yeah? Okay, if we draw lines. So if I said, okay, let's get rid of one of those lines from the list. This is literally repeating something that I've already taught. What happens? We go from 0 to 0, 1 to 1, and then what happens, what connection am I going from list A to list B?
1, 2.
Yeah, so 1 goes to 2. So what happens is 1 just gets repeated and it gets connected to 2, okay? Simple stuff, yeah? this is where it gets difficult. Branches in Grasshopper are kind of like ways Grasshopper says, I want to isolate this information to just itself, okay? So, for example, if I had a list of 2 groups, these 2 groups, okay? They're in their branches, separate branches. If I create the polyline, we've used Polyline, right? Have we? Okay, what Polyline does is if you've got a list of points, you plug that list of points into Polyline, it will effectively create a polyline between those points, okay? So a list by itself with 2 branches will mean that Polyline goes, okay, I'm going to just look at the first branch and work on the first branch. So therefore, it'll just create a polyline like so. And then it'll say, oh, okay, here's the next branch, I'll make a polyline, okay? So therefore, you've separated those 2 lists into 2 branches and they can work by themselves, yeah? So, if we think back to what we were just doing with the line connections though, if I had 2 lists with 2 branches, 2 sets of branches each, then it's going to end up being the same, yeah? It's going to create lines like so. But if I were to say, okay, I'm going to get rid of, no, that's a bad example. I'm going to get rid of this point, yeah? So if these were 2 flat lists, normally what would happen is this would connect and then this guy would connect, then this guy would connect, and then this one would end because this list has only got 3 in it, yeah? But what we've done is we've said this list is only going to work with this one. So it's going to go, okay, first list, connection. Where's the next connection going to go? I'm going to have to repeat this point, yeah? And so you can see that we can start controlling the way Grasshopper works using branches. A lot of the work that I end up doing in like actual Grasshopper coding is just trying to get my data into a structure that works. Because like once you learn how to do an offset, or once you learn how to connect lines, that's great, right? Then it's like, how do I connect lines in an intelligent way? It's using branches, that's the way, okay? So, a really important thing to note is, if I've got a list of points that are in a branch structure, and I've got a list of points that are not in a branch structure, meaning they are actually in a giant branch, yeah? What's going to actually happen is Grasshopper is going to say, let's look at branch 0. Okay, this is first branch. Let's look at the first branch on the other side. This is it. Okay, let's connect them up. Now let's look at the second branch. This is the second branch. Now, what happens when a Grasshopper has a list that is shorter than the other?
Starts again.
It starts again. It uses the last item.
Yeah.
So therefore, which is the last item, which is the last branch in list B? There's only one, right? So therefore, it'll use it again. And therefore, it'll do that. And then that. And that. Okay? So, what we have to do is, if we're working with branches, we need to make sure that our branch structures correlate with each other. So if we've got a flat list of points like so, we need to force them to end up being also in the exact same branch structure as the others, okay? So the process of taking branches and reducing them to just a single list is called flatten, and we've used it. I think I've like asked you guys to use it and said, look, we're just going to ignore what this is doing. It's just going to fix the problem for now, okay? And the opposite of that is called grafting, and this is why the tree metaphor kind of becomes really interesting, because what grafting does is it effectively produces a branch for each item in a list, okay? So if we had 4 items in 2 branches, and we graft those, what happens is we end up creating 2 branches, each with 2 branches in each branch. Okay, and this is where it starts getting really complicated, and we can avoid that. We're not dealing with that today. We probably will never deal with that in this course, okay? But what do we have here? There is a branch per curve, okay? If I want to now move this, like I want to take each of these curves and I want to put them flat on the ground, on the XY plane, what process would I use to do that?
Oh, we've done this.
Yes, we have. That's why I'm jogging your memories. Calvin? How you doing, man? Good. Shouldn't you be with Holger?
No, I'm not doing it.
Okay. See ya.
Is it plain to origin?
Think it's called orient. Do you remember orient? Yeah? What does orient require to work? It needs a geometry to orient. It needs a origin plane and a target plane or destination plane to take that object and move it, yeah? Everyone's familiar with orient? Okay. So which planes do we want to use as the origin planes?
Origin, the ones we've got now. So
Yeah,
Z.
we're slicing through this with planes, right? So we might as well use them to use as the target, as the origin plane, yeah? But let's have a look. We've got our B-rep plane intersection here. You guys are going to realize exactly why I explained all of this just now. So we've got our curves. Now, if we look at our planes, what do we think is the issue right now? Keeping in mind exactly what I just explained.
That the top is all single branch and the other one's all in one.
Exactly. Okay? Every curve that we've got is in a branch, and every plane that we've got is in its own, like a flat list. Okay? Now, what's one solution? Yeah, so we could flatten these curves. Now, in some circumstances, that is a good idea. Okay? We could flatten this list and we would just have a nice list, right? But what if we were producing more than 2 curves in here? We would end up with more curves than our planes would allow, right? So we actually probably want to do the opposite of flatten. We want to graft our planes. Now, I know I have the foreshadowing that we want to graft, because we're going to be doing something that actually requires those grafts to work as when we generate the slots, okay? So what we're going to do is graft our planes. You can graft 2 ways. You can either use this graph tree component, or you can right-click inputs and outputs and select the graft shortcut. In this case, let's use the graft component. So we're going to orient these. If we orient them to a single destination plane, we're going to have an issue, but let's just do it. So we orient from our target plane. Please be recording. We orient from our target planes to the origin. Our origin planes to the world X, Y. And we get overlaps, right? And that's because they're just all being oriented into the same place. So we're going to generate some planes that actually help separate these. So to do that, how many planes do we want to make?
As many as we've got.
So let's count how many we've got. Let's use list length. Have we used this yet? Okay, good. That means I can explain it. List length is very simple. It tells you how many items you have in a list. Very useful. Very, very useful. Because now we know we've got 9 sections, or not just 9, sorry, we've got 9 planes cutting through our object, so we might end up with more than 9 curves. But what we can do then is use the series component. We've all used series, right? Not the iPhone assistant. One laugh. I got one snicker. That's all I need. With the dad jokes. Okay, so if we use series and we count, we plug our 9 into the count, the actual list length, that's going to give us 9 numbers, or however many planes we've made. So if you guys want to change the number of planes, you can do that in the range, and that's going to filter through to your series. So you don't need to double check you've got the right number. And if we chuck some sliders into that, let's create a slider that goes from 0 to 50. That seems reasonable. And we're going to copy that twice. I mean, not twice, just once. So that's going to go into the start, and the other slider is going to go into N, the step. So we are then going to generate points along the y-axis. So we'll use a construct point and plug our numbers into y, so you can see our points running up there. As I move my slider up and down, that just changes the spacing between the points, and the start slider changes the start origin for that. Excellent. We're there. So we're going to use the same technique we've used at the beginning, near the beginning of the script, where we generated points and placed planes. We're going to then place X, Y planes at each point. And then we're going to plug those into orient. And just be careful, because remember the way the data structures work? We've got a flat list here. And we've got grafted lists in branches here, so we need to make sure that we graft our XY planes before we plug that into the orient. And that should then, why is that not working properly? Oh, there we go. And that will then spread our planes apart, for our sections apart, so that they don't collide. Pardon? I just upped see this slider? I just ramped that up a bit so that they don't. Cool.
My one is a little bit weird.
A little bit what? Dude, just hide everything. Huh? It's up. Are you using the right plane? Are you using XY?
Yeah, XY.
Yeah, guys, just look at your Y, look at Woody, look at your Y going into B. Does it look different to the others? See, you'll have a dashed Y going into G and a dashed Y going into A.
Yeah.
What type of dash does the BY have? Okay, so what Woody's done is he's plugged his plane in like this, right? And therefore it's created this outcome. What that's doing is effectively, you remember how I drew lines between every point and every point? That's effectively what that's doing. It's putting looking at this and saying, okay, I'm going to place this object from this plane at all of these points, and so on and so forth. So just remember, you've got to graft that tree before you plug in. This gets really dangerous, okay? Because if I had 10 curves with 10 planes and another 10 planes, right? Then what's the potential outcome that my cross-referencing could generate in terms of plane manipulation? Yeah, I could produce more than 100. I could produce 1,000, yeah? Just from 10 objects, 10 planes, and 10 planes. 1,000's not so bad for a computer, yeah? But all I need to do is make that 10 planes 100, and that same process is going to go from 100 to 100 times 100 is 10,000, and then it would go to like 10 million, I think, or a million, right? So, and that's when the computer starts going, right? So just be really careful with this stuff, guys. Like, it can crash your computer. So just, you want to start saving this stuff. For example, I haven't saved my script, and therefore it's not going to autosave. So just remember, very quickly, we want to save our scripts. It's week 6, right?
Yeah.
Wow, look at us go. We're halfway through. Okay, so is that working for everyone? Excellent. Let's stick with the plan. Let's finish one direction first, okay? So what's the next step?
Create points along the curve for where we pick up.
We've got to put slots in.
Yeah.
Yeah? Yeah, that's what you're trying to say, right? Yep.
Just along the way.
We're gonna try and put slots in. So this is where actually I'm wrong. This is where I'm wrong. So for us to put slots in, where would those slots go? Where we're cutting in the other direction, the opposite direction. I ask really simple questions, I know.
That's why I'm not saying it.
Yeah, no, but it's meant to be a conversation. What I'm trying to do, when I ask these super dumb, simple questions, it's just trying to keep you guys engaged and be like, oh, this isn't actually as hard as what it needs, like as complex as what it needs to be, right? Because actually, it's pretty straightforward, yeah? It's just hard to get your head around it. Cool? So if we're cutting in the opposite direction, that's where our slots need to be. And so therefore, we do actually have to start the opposite direction's script for us to be able to then put the slots in. Okay? So what we're going to do is we are going to do the opposite direction right now. The only difference between the X direction and the Y direction is we are constructing points using the Y domain. They need to go on the Y construct point. What I'm going to do is just group all the objects that I think are going to, like, I'm going to highlight them and just explain why they're the ones that we need to change. They're going to be cutting the XZ plane instead of the YZ plane. And we probably want to start our construct point, like, we're going to slice them and put them off to the side, right? So we're probably going to change something in this particular component as well. So let's group those together. So these three objects,
How did you do that, sorry?
I selected them and typed Control G, and then if you double click a group, it'll change the way that it displays the group. Cool? So these three objects are probably going to change in the process, okay? So what we're going to do is we're going to highlight our range. Actually, what we can do is actually just highlight the range, hold Control Shift and press right, and what that will do is select upstream.
Oh, yeah.
Huh? Does that make sense?
Yeah. Sorry.
Cool. So that's not going to select these things because they're not upstream of it. They're actually like a branch back. We're then going to copy and paste. And for some reason that doesn't copy and paste the group. If any of you are actually grouping, using the group to help identify, we also want to select the group and then copy and paste. Okay, so what we're going to do is instead of plugging X into our range, we are now going to plug Y. Then, instead of the color index plugging into the construct points X, we need to change X to Y on the construct point. Then, instead of using the YZ plane, we need to go get the XZ plane and replace that. So I'm going to hold Control Shift and unplug everything, the input and the output of YZ, and plug that into the new XZ plane. And then we're almost there. The construct point that we're using to make the planes, that's probably, depending on where your object is, it might not be in a point, like in a place that it might collide with our other object. So we're just going to grab a slider. I'm going to write 0 to 1,000. And we'll plug that into the X of that. So that way we can control and slide that section away and just keep it separate.
Yeah. Pushes to the side.
Huh?
Goes to the side.
Yeah.
So mine is just identical.
You sure about that?
When they look at.
Well, it makes sense, kind of.
No, it doesn't.
If they're identical going the other way.
No, it doesn't make sense.
What?
You,
Aren't you essentially just repeating the same shape and then it's just...
no, unless you've made a paraboloid and not a hyperbolic one.
I'm working off a like four-sided shape.
Is it flat?
Yeah.
Oh yeah, that makes sense. Yeah.
Yeah.
Yeah, it's symmetrical.
Yeah, that's
Yeah, no, I thought you were doing something else.
I was like, if I've been doing my shape on the whole
My shape is going to
Pardon?
my shape is going to this way, not plating to the original.
Okay, are you using an XZ plane there, man? You need to use XY plane. Which way is Z? Which way does Z point? Yeah, so you're moving your objects from a 3D plane to the XZ plane, not the XY plane. Does that make sense?
I just guessed the wrong one. You say I need to like replace someone with like XZ.
Oh, no, it's this one that you need.
Oh,
Yeah.
it's the wrong one.
So XZ needs to go here. Hold Control Shift or Command Shift or whatever you need. Done. Cool. That was easy, wasn't it? all we did was we took the process that we just did and we changed the orientation of it. That's it. Okay? That's all we did. Broken?
Why is only cut through just the half one?
So it's just cut half of the. And one is kind of maybe.
Oh. See, okay, guys, just remember that if we use, we're changing every direction, right? So you've just missed one step. This component here is telling us what the x direction is. If we use the x coordinates and not the y, then it's not going to divide it along the y appropriately, yeah? So we want to use the y domain for our second range. Is it working now? How about you? Yes?
So after we paste, it didn't grow. Is that
Okay, just guys, everything in purple right now is going to need to change in some way, okay? So we're using the y coordinate, right? Then that's being plugged into the y coordinate of the construct point. What coordinate are you using? X, right? Yeah? It's so easy to debug these scripts.
So out of our deconstruct box, we still want to take the X, or we want to make that come out the Y now?
We want it to come out of Y.
Okay.
It's probably working for you because yours is symmetrical around 0.
Yeah.
But yeah, you do want it to be like if it moves or you want to use the script on another project. We start seeing all the interior designers doing waffles. And it's true. Like, have you guys heard of lava? They call themselves an architecture firm, but they pretty much only do interior design.
So we don't want the extrude going down. We don't want to copy the extrude, do we?
No.
No.
Like,
So that's coming out of.
this is in Surrey Hills. It's a waffle script, right? It's it's a waffle script. Not lava. Puerto del Sol? No. this is probably like the most subtle way of using this actual process. But do you see how like the face of this wall has like a little curvy lip, right? It's just a waffle script that's doing that. Like they're doing the least crazy thing you could possibly do with a waffle script, but that's the waffle script there. Cox, Washington Embassy. We never published that. You see them a lot. You see you're going to see waffles a lot. They're really easy to do, and they're cheap because you just make them out of flats, like they're flat objects basically, and they can make geometries that are quite cool. Okay, what were we doing? We were waiting for everyone. Everyone's there? Everyone's good? No? Come on, Woody. Come on. We're all good? Good? We're good? You good? You good? You're good? I love your little Domokun. We're good? You don't know Domokun?
Unless it's like 5 or something.
Yeah, 9.
Okay, I'll show you guys. Good? Woody? Come on, Woody.
Basically 4 bits.
Yeah, that's what I was working with before.
May I take over for a sec? There's,
I'm gonna go, yeah, because I think
it's just like the ultimate.
yeah. That should be offset. No, just do something with your plane.
okay, this isn't generating sections, right? Because you're plugging XY in, yeah? That actually should be XZ.
From here. And then you need like a midpoint here. So shift the midpoint.
Oh, instead of Y sections.
Yeah, when we do the line.
Yeah, so there's your sections through there, all right?
Yeah.
I think that's the only way that
So there's one,
Because I'm assuming you have to
and there's the other.
Sorry,
Is that actually good?
what are you trying
Okay, and then that should be plugged into Y,
to... Down
man.
to Y, yeah. Where did I put it? I didn't do one.
And we want to be using the Y domain.
That's one. Oh, that's one that pushes
Cool.
up to the, yeah. So it goes into X.
Does that make sense?
Yeah.
And make it,
So what that's doing is it's going to cut through our object
to make it 1 to 1,000.
like so,
1,000.
yeah? And therefore it's giving us that.
Yep.
Cool?
Yep. Oh, meant to cut it.
And just be careful with that start number as well. So this start number, like we keep these two as a different number, then we can like move, oops, sorry. Not that number, that one. We can control the distance away. Okay, we're good, we're good. UN's good, standard's good. What's your name, Standard? Roy, okay, okay, good. Well, I'll get to know you all by the end. The closer you sit to me, the easier it will be for me to remember your names.
Yeah, it's not like this, but don't think it's works.
Sorry? Can you say that louder?
So I think it doesn't work as yours.
It doesn't work. Let's find out. Okay, we are cutting an XY plane. No, that's good. That's what we want, I think. Nope, that is not what we want. Okay, so this plane here, what plane is that? Right, is that the plane that we want to cut through our objects? You sure? If we're cutting planes like this, and the XY plane is like this, is that the plane that we want to cut through our object? You think so? Hang on. We want to cut our objects this way and this way, and you're using a plane that's doing this. Is that the right plane? Right. So we want to be using the XZ plane. So you see how that's cutting through our object like so. And now that's working. And that's working. Excellent. Okay, so you just need to space that out differently. Cool? Okay, guys, we've got our two sets, right? Now let's put slots in them. We've got an hour to put slots in. We're good. We're good. Yes?
Yeah, my fault is red.
This one they have a center line.
What do you mean, man? It looks fine. It looks good.
I mean, like for this like arrangement, they have like a center axis for the pattern, but this one they don't have it.
That's fine.
Okay.
That's actually. Is this centered? Does this object look symmetrical in one direction?
Yeah,
Is it symmetrical this way?
I think so.
And then look the other direction. Is that symmetrical?
Oh yeah.
Does that make sense? Why that's not on a center line now?
Oh yeah.
Okay, good. So you're fine. It's fine. I gotta leaving my drink. We're good. We're good. We're all good. Okay, let's put slots in. So, if I have planes and I have surfaces, what can I get with an intersection from those two objects? It's very simple. It's like we've already done it. If I intersect a plane and a surface, what do I get?
Okay.
Right. So, these objects here, I'm going to hide everything and just isolate the first set of intersecting curves. Okay, these guys here, they're curves at the moment. But what we can do is we can make them into surfaces. And the surface that we can make is a boundary surface. Boundary surfaces require a closed curve that is planar. Now, what are we guaranteed to produce from the intersection between a solid and a plane? We are guaranteed a closed curve because it's a solid object, right? And it's going to be planar because we're using a plane, yeah? So plugging curves into boundary surface is going to give us a whole bunch of trimmed surfaces. I'm going to separate these more. Okay, so these planes here, the XZ plane of the opposite direction, those are the planes that we want to find intersecting with our surfaces, because that is the plane that's going to actually intersect. So let's grab, I'm talking in circles, let's grab the plane parameter component and plug our XZ planes into that. And then we're going to bring that up and use that in the first section. So we'll call the first set of curved intersections A and the second set B. So we're going to bring the planes that we've generated in B up into A.
What did you grab, sorry? Parameter.
We're going to, the plane parameter component. it'll just store planes in it itself. Okay, so I'm just going to rename that. I'm going to call it B planes, just so that we don't get lost. Cool. Okay, so what have we got? We've got a grafted list of trimmed surfaces, and we have a non-grafted list of planes. Usually, in most circumstances, we have a problem because one list is not grafted and the other list is. Yeah? But we want all of these planes to intersect every curve, every surface, yeah? We don't want this plane to only intersect this surface and this plane to only intersect this one and so on and so forth, yeah? So we actually have the benefit of one list being grafted and the other one not. So therefore, we can actually utilize the process that Grasshopper uses when that occurs to create the cross-reference, right? So every plane will intersect every surface. So let's not flatten our surfaces and let's not graft our planes, and instead let's create an intersection between a B-rep and our planes. Why did that break? That's fine. Okay. So what we can see is we're starting to see those lines appear, right? On our surfaces. But we've got one problem. We're starting to get really fucked up branch structure, okay? No, it's super fucked up, okay? So it's confusing. Actually, if you actually know what these little numbers mean at the top of the branches, you'd be like, fuck, this is so confusing. There's so much data there. So for one, Grasshopper adds branches to things unnecessarily. It's mainly just so that you can keep track of things if you really want the head fuck to keep track of it. In this case, what we can do is we can use this thing called Simplified Tree. What that does is it gets rid of all the unnecessary zeros, any unused branches in that structure. And what you'll note that it's now going to reduce that down to two branches. Okay. Now, what we've done is we've done that cross-reference, right? But what Grasshopper has said is gone. Remember how it was compensating for if we were to produce a intersection with an object that had more than one curve as an outcome, it would create a branch to put those two curves into that one branch. It's doing that again. So even though we've done the cross-reference, it's then going, okay, every plane that intersects my surface, we're going to give that an extra branch to place that curve. And that's too much for us. So we're going to do the reversive graft. The reversive graft is not flatten. Flatten destroys all branches, okay? It takes every branch and just basically flattens it all into one. But what we want to do is take one step backwards in the graft, okay? And I have a very awesome plugin that gives me a very strong component that does that. It's called Shift Paths. You don't have that plugin. You can use the inferior version of that called shift paths. It's just pink instead of green. Okay, so go grab the pink shift paths. It pretty much does exactly what my superior one does, except my superior one has little checks in it that stops it from breaking. So this can break, just be careful with that. What that's going to do is it's just going to reduce the amount of paths in your branch by 1. So the default in that is -1. So we want to leave that default there after we've simplified. And what we'll note now is how many branches do we have? How many branches do I have?
8?
No. 9. Yeah? I have 9 branches. And how many surfaces do I have?
Lots. No.
I have 9. Right? So each branch has a variable amount of curves. We can see this particular branch here only has 1. Check it out. This particular surface only has 1 slot in it, right? So that's probably correlating with that surface. And as I go into the middle of my object, I get more slots, and therefore, as I go to the middle of my list, I've got more slots. Does that make sense? Okay, so each branch is effectively a group that corresponds to the surface in our process, okay? What this means is this orient is actually working with branches, yeah? I've got a branch here, I've got a branch structure here that has 1 plane per branch. So I can actually orient all my curves that I've been working with in that same structure, right? So all I have to do is copy and paste and plug all my straight lines into that. Now if I preview the output of this, that's going to place all of those slot curves exactly where they need to go relative to our oriented boundaries.
One's not done that. Oh, I just shut that one. Oh, it has done that, sorry, ignore me.
See why it's like, oh, we've got to reprogram how we think a little bit? Yeah. If we had flattened our list prior and used a flat set of curves to orient, then we wouldn't be able to move all these lines, because each line would then be like a separate line for each plane and they wouldn't orient into the same place, okay? Now, the beauty of this particular process is that we can now do all the functions that we want to do to our slots on the XY plane instead of doing it on the 3D plane that we're working with, okay? So offsetting is much easier in 2D, and doing like Boolean functions are much easier. And in this case, we probably don't even have to do Boolean functions. So, what are we going to do now? We've got our lines. If I cut this right now, I would get lots of little plywood sections, yeah? It wouldn't work. So what are we going to do?
Shadow the lines.
Yep, shadow them. And where are we going to shadow them?
About 50%.
Yeah. So we are going to use shatter, and we are going to reparameterize our curves, and we're going to shatter them at 0.5. And then we are going to pick one side. So let's pick item 0, which happens to be the bottom. which is going to leave us with these lines to generate slots. Oh, it's already looking like a waffle if we were to make it out of paper. By the way, guys, this particular process has actually, because it's quite easy to code, like a robust script for this, there are like programs that do this for you. I think there was one called 123D Make that was discontinued. But there are programs that actually do this. It's for like home makers, basically, like people who are do-it-yourself crafty type people that want to make cardboard objects at home. I would recommend that if you want to be a professional designer that uses these techniques, that you keep using this scripting method to do this instead of using those services, because it effectively, a lot of the techniques that we use here to make a plywood waffle translate into standardizing geometries for steelwork and making facades and roofs and blah, blah, blah. And for example, the plywood cutting that Lava did in Surrey Hills to Puerto del Sol's facade, internal finish to their bar. The programs that provide this stuff for free aren't very good at then translating to like Revit or steel fabricator, blah, blah, blah. So it is like, if you want to use these techniques, you got to know how to translate that in a professional environment. So just avoid those programs.
Mine's not all of them are on the bottom.
Some of them are swapping around?
They're not swapping around.
Some are on the top and some are on the bottom? Yeah. Okay. So what that is that's because the line that's generated is actually being generated from the bottom to the top or the top to the bottom, right? So what needs to happen, guys, is we can put in a check to make sure that our lines are all going in the same direction. Now, in this particular example, all the planes that we are generating are vertical. So that means the lines that we are generating are going to be vertical. Yeah? They're always going to be going up and down. So at the point where we shift our paths, we can put in a process. Actually, no, let's do it. Let's do it here. At the point just before shifting paths, we can put in a evaluate length function.
Where does the plane connect to the plane?
It connects to the. It's these planes here from here. Okay, we're going to evaluate length. What we're going to do is get the simplified list and evaluate the lengths at 0 and 1, making sure that we turn on multi-line data, and also making sure that the C input of our evaluate length is reparameterized, because that really should be default. What that does is it's going to give us the start and end point of all our lines, yeah? And the important thing is we're using this process instead of using endpoints, because what endpoints does is it outputs the start and end point of your line in two separate lists, whilst because we've got a grafted list, our evaluate length component is going to give both our points in one single list. And this, we're actually going to do something that I just explained earlier. So we've got 2 points per list, and the 2 points describes the start and end point of our line, okay? What we can do, and this is going to start, we're layering a lot of information on your brains today, but it'll work out. If you grab the deconstruct point function, what that does is it will give you the x, y, and z values of your points. We care about the z values. So with the z values, we will then sort them, which will then sort them, as you'd expect. But at the same time, synchronously, we are also going to sort our points. So what that means is, if I were to take a list of all your ages, right, and I were to sort that list from youngest to oldest, with probably me being the oldest, like if we include me, right? All I'm doing is sorting the numbers, right? I would have to, if I wanted to also like know who's who, I would need a list of all your names in correlation with those numbers, and I would have to also sort them with the numbers of your ages, right? So what we're doing is we're sorting the height values of the points, and at the same time we're also sorting the points using that same order, okay? So, for example, if I were to take this row of people, including myself, and sort them by their age, we would take all their ages, sort them, and then we would have to then pick up each person and move them, and I would then end up be sitting at the very end, right? So sorting synchronously is sorting objects at the same time as their correlated values. And you will break this component. It will not work if it has a different number of items going into the A, okay? What that means though is out of A, our points are going to be sorted from bottom to top. And so if we then create polylines on that from the A output, and we then plug those polylines into our shift paths, those of you who are having issues with the jumbled order of points, we've now fixed that.
Well, it goes into that shift path that we did ages ago.
Pardon?
It's going into the shift path that's coming out of.
So we're basically taking the curves that come out of Simplified Tree, we're plugging them into evaluate length, and the polyline from that little process is going to be plugged into the input of shift paths. So we've just surgically put in a little check to make sure that all our lines are going from a low Z value to a high Z value. Does that make sense?
My polyline's got narrow though.
That's fine. So does mine. The error says insufficient points for a polyline, right?
It says, no, it says resulting polyline, and then, oh no. Yeah, that's what it says.
Insufficient points? Yeah. What that's basically doing is it's saying, hey, look, check this branch out. Check out my branch. How many points are in that branch? There's 0. I can't make a polyline from 0. That's what it's saying. This one here is going, hey, I've broken. Intersection failed. I can't find any intersection between this plane and your surface. That's because we've got like a plane over here trying to intersect that surface, but it's like there is no intersection. And for some reason, it's decided that that's a red error, but we don't really care. Like we don't, it's cool that there's no intersection, that's fine. Okay, so is that working for everyone? Excellent. Okay, so now let's go back to the list item. What we need to do is turn this into a slot. Okay, so we need to consider the planes that we've intersected our object are going to be defining the center plane of our plywood. So that means the slot that we need to produce has to use this line as a center line and not as an edge, which means when we offset this, and we'll go grab offset curve. When we offset this, we actually want it to only offset 50% of the width that we need it to offset. So, and we need it to offset in both directions. So that means we need 2 offsets. We need a slider. So I'm going to create a slider that goes up to 6 mil because I might make mine out of 6 mil ply. We're going to plug 3 mil variable into both offsets, but the first offset we want to go backwards. So we're going to plug into the expression there minus x divided by 2. So that means when I plug 3 millimeters into that, it's going to convert that to minus 1.5. And I'm going to paste the expression into this component panel. And then we also want the expression for the second offset to be not minus x divided by 2, but x divided by 2, which will then give us a centerline relationship as we slide this up and down. So this number slider will then define the width between the 2 offsets, yeah? Using that initial line as the center line. Cool. Got a problem. Huh? Look at that, almost done. Okay guys, I've been a bit generous with time, so we're just going to finish this off, okay? So, right now there's an issue. We've made a mistake. There's a problem that we're going to have to go back and fix, but I'm going to get you guys to work that out once we get to the very end, because it won't take much to actually fix it. So now that we've got the 2 offset curves, the beauty of the offset curve is it actually it does graft. It grafts the objects as it goes through. Do you know why it does that? Can anyone have a guess as to why it grafts? Why did the plane and BREP intersection create branches? Why did it graft? Anyone? Guys, when we used the plane and BREP intersection, why did it graft the output? Why is your component grafting it? Why is it putting it into separate branches? Yep, why is it grafting? When I cut a plane through an object, why does it graft the outcome? How many possible curves could I get from my object? This particular object. 2, right? So why is it grafting them? To help compartmentalize those into that group. You know, it's grouping them, right? Okay, so why would offset do the same thing? Offset's doing the exact same thing. Why? if I offset this curve, what do I get as an outcome? I just get either a bigger or smaller version of it, yeah? Okay, if I offset this curve, how many outcomes could I get if I go positive? I get 1, right? But if I go negative, I get 2 curves. And so it's automatically saying this could produce more than one outcome for that one curve. So we're going to create groups, branches for that. So that belongs to the branch. That's why it's doing it, okay? We're going to utilize that because offsetting lines isn't going to produce more than one line. We're going to utilize that because what that's doing is at least it's forcing all of our lines to be in separate branches. So then when we use the loft component, it only lofts between each corresponding line. And we're going to cheat and get the boundary curve of the loft. And the way to do that is literally by plugging the loft into a curve parameter, which will immediately go and grab us the curve output of the surface instead of a surface. Okay, what? How did you do that? That was too quick. Okay, so I've plugged the 2 offset curves into a loft, and then I've plugged that loft into a curve parameter. And what we're doing is we're actually utilizing a little code that's written into curve that tests if the object is a curve or not. And if it isn't, it tries its hardest to make it a curve. And in the case of a surface, it just grabs its boundary edge. So that's a nice little shortcut. Okay. Can anyone identify a problem?
Yeah.
What's the problem? Huh?
You cut square instead of cutting all the way through.
Yeah, so because we're using the center line to generate the slot, the center line, because the center line only goes from here to there, let's turn off grid snap. Because the center line only goes from that point up, when we offset that, in this case it's overshooting, and to be honest, we don't really care if it overshoots. And in the other case, it doesn't overshoot. So we need to write in a compensation for that, or otherwise there's no way we're going to be able to slot these 2 objects together because there's going to be a piece of timber in the way, yeah? So what we're going to do is before we shatter our curve, we just need to extend it. And we've used extend curve already. We've already used extend curve extensively. So I'm going to let you guys plug away at that. Just be mindful that when we use extend curve with the shatter, we probably actually want to extend in both directions because if we only extend in one, that's going to change the location of where the midpoint is. So by extending it, we can then identify exactly how much extra we need that to be before it works. And you know what? Right now, if you bake the curves out here and you bake the orient here, that's actually laser cuttable. You don't need to do any Boolean function on this. Like you don't need to cut one away from the other because the laser cutter is going to do that for you. So we should finish this, right? We've got the other direction. So I kind of want to get you guys to do that by yourselves. I get this shocked look like, what? You expect me to do exactly what I just did on something in the other direction? Okay, so what we're going to do see this the boundary surface and the B-plane components? These two components are effectively the start of the slot script, yeah? We got that? So if we just copy and paste, if we Control Shift and select upstream, that's going to highlight everything that we need to copy down. Actually, that's probably not an appropriate way. We need to copy all of this down, okay? We need to copy the, what's a sensible way of doing this? Hold up. Everything after the orient. So if we go Control Shift and select right of orient, select everything and then deselect orient, and then we're just going to slide that down a bit, okay, just to keep it separate. So everything between the boundary surface and the planes and the orient, so basically all of this stuff, not the orient itself, we're going to copy. Okay?
How do you deselect it?
You hold Control and then you select.
Yeah.
We're going to copy that down. We're going to rename B-planes A-planes. We are going to connect the XZ planes from the A section into A-planes, because we need to use those instead now. And we're going to plug our B-rep plane intersection from the B section into the boundary surface, because that's the new input that we need to use. And what that should do is at least give us, like, we can now just check that's giving us the right result. Look at that, it looks like a waffle. That's exactly what we can do for the final half hour, is help you guys actually render this properly.
Zoom's not working for some reason.
Zoom.
Yeah. Oh, there you go. It's working.
Okay, are we all there?
No.
We're not there? So it's just as simple as we're copying down this section. So from boundary surfaces and B-planes or A-planes through to the shift paths, we're copying that down. We're replacing the curves that go into the boundary surface with the sections going the opposite direction. And then we are plugging the planes, the XZ planes, into the A plane or B plane component, and we're renaming that component to say A plane so that we don't. So we've just got like a nice little sensible guide there for ourselves. Do you get what we're doing? Yeah? Good. Okay. Then at that point, we can easily just copy our orient for the B section and then plug our shift paths into that, and that should work, right? So now if I look at the orient, these two orients that I've created, they should create that line segments again, just like the A part of the script. And then all we have to do is copy everything from the A section beyond the orient So if we copy that down and plug that into our B section's orient, the only difference that we need to now change here is instead of picking the first item from after shattering, we need to pick the second item, which we can either use 1 or -1 to pick that. So I'll just use 1. It's also at this point that we can just double check a few things because we're pretty much finished. For example, our planes aren't 3D, so they're not gonna identify if there's gonna be clashes. So for example, we can see here if this piece was just a little bit longer, like if it was just that much longer, then our plane wouldn't intersect it, and therefore it wouldn't create a slot, yeah? But at the same time, this would clash with our plywood. So just double check those things. And we just need to hide everything that doesn't need to be cut, and we're good. Cool? No. So what I did was I just copied everything after this orient down.
Yeah.
I plugged in my new oriented lines into the extend curve. Then instead of using the number 0 after the shatter, we just need to pick item 1. Cool? Woody. Cool? No, I'm not cool. It's not working. Okay, so last little steps, and this is purely just for like rendering, okay?
So rather confused, I'm taking.
Okay, let me just do this and then I'll walk around. So these boundary surfaces, they're really all that we need to deal with for the render, right? So super cheats way, right, is if we take these boundary surfaces and bake them. So I'll just bake them onto layer 2 at the moment. And then if I select those in Rhino 6, that's right, not all of us using Rhino 6, right? Okay. Huh?
I have Rhino 6.
Is everyone using Rhino 6? Everyone? Okay. Then in Rhino 6, if you go to the object's properties, you can get properties. It's this little rainbow icon, like the rainbow wheel. You can see under properties, there's thickness. We can set in that a both-sided thickness, turn it on, and then set that to 1.5, I believe. And that will give us a good enough 3D model to screenshot and render for the report. Cool? Like that's pretty decent. There are other ways to do it, but I want to walk around and make sure everyone's good. And we can do that another day. doing renders, the art of doing computer graphics is all about lying. Like it's just a complete lie, okay? Like it's all smoke and mirrors. If you can create a shortcut to get something to work faster and better, then you're going to use that shortcut. It's the complete opposite to actually drawing stuff for construction, because if you don't work something out and then it goes to construction, it's like, fuck, like this doesn't actually work. But in this case, because all this is an image, we can take shortcuts and just, like these don't actually have the slots in them that we need to represent, but that's cool. We don't need to put that in the actual render. We just have to render what the actual final outcome will look like. Cool, okay, so, Joseph, you good?
No. So I tried to start again.
Right.
And
Why are you always starting again?
no, not start again, but I've deleted my copy and paste and I tried again. But I seem to be taking.
Okay, just undo it.
Yeah. Oh yeah.
Okay, so you've got to the point where let's just slide this down. So this point here is, and can you hold shift? This point here is where we want to copy.
Yep.
So copy and paste. So we are using these curves for the boundary surface.
Yep.
And we are using these planes to do the intersect.
Right. Yeah.
Yeah?
That makes sense.
Then we want to use this orient, so copy and paste that one. Paste. And then everything after the
Goes in,
orient
Yep.
is what we need to use.
Yep.
So copy and paste that.
That goes into there.
But all that we need to change here is
Exact. One.
done.
Beautiful. Thanks.
Yeah. Huh? The curve, you just hit it. It's hidden. It's just here, man. There it is. What have you lost? You don't. You haven't copied it. You've. There it is. There.
Oh, okay.
Cool. Yes. Huh?
On the A curve. Wait,
Is that A or is that A?
that's A.
Okay. So the first set isn't working, is what you're telling me? Is that?
What do you mean first set? So basically, it's just when I
Hang on,
copy
hang on.
down those things.
That's A. This one's A.
Ah, okay.
I don't think the angles will work.
This one's B.
Okay.
Because you
Okay, yeah, it's not generating. So we've got you're using using the right surface. You're using the wrong planes to intersect. So we want to use. You know how we've used these planes for this one.
Ah, okay.
We want to use
So
these planes for the bottom one. Ta-da! Good job. Yep.
Like for, it's not connect quite well, it's okay for the laser.
What do you mean?
So you can see it's how the whole shape, how it connect together, because sometimes it can be like
Oh, because you're doing it in separate segments?
yeah,
That's fine.
that's fine.
I don't mind.
Yeah.
Cool. But if you want to work out how to, well, you could, if you join all those surfaces together and use that joined surface for your waffle, then they will connect. Does that make sense?
Not really.
Okay. Let me show you. Let me show you. Can you isolate? Get all these four surfaces.
Isolate all.
Can you find them all? Are they? They're in that, right?
Yeah.
Now use join surface on that. B-rep join. Yeah, you had it. It's the second one. So plug those into that. And just flatten the input, like flatten B. Right click B. Flatten it. What's the output from the output B? Make a Yep. Ooh, okay. Yeah. You're gonna have to. They're not touching perfectly,
Yeah.
so you're gonna have to just do what you have been doing. Yeah. Hello. You've got that line. Interesting. It's because you've plugged both these curves and these curves. You just want to plug those curves. Who is the master? I'm the master. Hello.
I think I did all, but it didn't seem like it didn't have any.
Doesn't have slots? Let's find out why. There's your boundary surface, and there's your planes, and your planes are creating intersections. Yeah, so it's creating intersections. Okay, so see this output?
Yep.
This is sorting the numbers,
Yep.
and this is sorting the points. And you've grabbed the numbers, not the points. And so then ta-da! Cool. And so the same needs to apply here. Ta-da! Cool.
Got it. Thank you.
Excellent.